I want to begin today by talking about quantum mechanics. Now, the course is not going to deal with quantum mechanics, but only to the extent that I will review it, that we will need it to understand the behavior of solids, the electronic behavior. I trust that most of you who will be taking this course have some prerequisite knowledge of quantum mechanics at a physics course level. If you don't have, you won't lose much, because the emphasis on this course is on the materials aspects and not so much on the quantum mechanics physics side of it. So I'll go through a quick review of the basic topics of quantum mechanics, and then we will launch into what we have seen so far is the classical understanding of the properties of materials. And now, by laying this sort of a bridge, how quantum mechanics changed that whole picture, that we had to rethink all that we know in the past. It was sufficient up to a point, but there were many things which we couldn't explain. And so how quantum mechanics serves as a bridge to bring us to a modern understanding of materials. So we'll begin with a quick review of some of the topics. I'll cover some of it today and perhaps some of it in the next class. My purpose is not to give you the mathematical know-how, how to solve all the equations and things like that, but just enough to lay a framework for us to understand. The classical picture we had so far allowed us to explain many things about materials, but one thing in particular that we'll take 2-3 examples. Say, for example, light. The classical picture we had was that light is a wave, right? And we could explain a number of different phenomena, for example, like reflection, refraction, interference, diffraction. Common everyday phenomena could be explained rather easily by treating light as a wave. And this idea was very, very popular, and there were a number of proponents. Huygens was one of those way back. And there were competing theories, one of which came in particular from Newton, which was a sort of a particle-like theory. But then this guy proposed that light is like a wave. Newton had opposing ideas. He called them the corpuscular theory. So light actually consists of particles called corpuscles, and the different colors we get because there are different colored corpuscles. Right? That was the idea. But a man by the name of Maxwell came along and derived a mathematical treatment that seemed to support Huygens' wave approach much more than it did Newton's corpuscular. So the majority of scientists in the probably late 19th century swung towards Huygens' wave approach, and the corpuscular theory was completely forgotten and ignored as an old idea. And we'll see how things swing around later, but this is the Maxwell's equations that were the classical equations of electromagnetics that laid the foundation for us in understanding the relationship between electricity and magnetism. And then what Maxwell was able to show is that light is an electromagnetic wave. So most of the developments after that were using this idea of light as a wave. And his idea was that light is an electromagnetic wave where we can portray it as propagating in a certain direction, which we call x, and then we have the electric field vibrating perpendicular to it. Okay? So there's the electric field that is vibrating perpendicular to this. And you also have a magnetic field which is now coming out of the plane, perpendicular to both these directions. So if we call this direction y, then my electric field is Ey. And you can also have a magnetic field that is perpendicular to this, which we will call Bz. All right? So this was the classical picture, excuse me, that was there in the turn of the last century, beginning of the 1900s. And you can express simply by looking at the electric field. The magnetic field can be treated exactly the same way, but we can express the electric field, its time and spatial dependence. How does it vary with time and how does it vary in space, by using a very simple expression, a sinusoidal wave, where k is what is referred to as the wave number, and it is given by 2 pi by lambda, where lambda is the wavelength. and you have omega, which is angular frequency, given to us by 2 pi nu. Okay? So what this equation tells us is that we have a sinusoidal wave traveling in the x direction, varying in its intensity and varying in its time dependence. With time it varies and with space it varies. That's what this expression here tells us. We can give a velocity to this wave that is traveling. Strictly speaking, we are talking of a wave packet that is traveling and not a single wave. And so the idea that we have here is this c is what is called a group velocity or a phase velocity. It's a packet of waves that is traveling together. So c, which is the velocity, is given to us by omega by k. Those are the two terms that we had here in the previous equation, the wave number and the angular frequency. So the group velocity or phase velocity is given to us, c is equal to omega by k, which can then be expressed in terms of nu and lambda in very familiar terminology, the frequency times the wavelength. We can also express an intensity term for this wave. How intense is the wave? And the intensity is defined as the energy per unit area per unit time. And so in this classical picture, we have intensity is equal to half c epsilon naught e squared, e naught squared, where the epsilon naught is what is called the absolute permittivity. Permittivity of free space, basically. Okay? So this is what gives me the intensity of the wave. It's square of the amplitude in the classical picture that we start with. So it was nice to describe many things, for example, like interference. So if you pass light through slits, and you have one slit, and then you have two slits, and so on. The Young's famous experiment you've all probably heard of in optics. Instead of what we find is we get an interference pattern of a periodic dark white kind of spacing, well known. And the idea that light is propagating as a wave explains this very easily. So interference we have no problem with. Young's two-slit experiment, as it's called. We get a periodic change in the intensity there. You could also explain things like diffraction. The same idea is used. Wherever we have dark areas, we are having destructive interference between two waves. Where there are bright areas in between here, that's where we are having constructive interference. And so the idea was applied to diffraction when we have, for any electromagnetic wave, and we'll get that when it is shining onto an array of atoms, for example, we will get a phenomena called diffraction, which is again related to the constructive or destructive interference of the waves that are coming from the different planes. The path length is different, you can calculate that and so on. I won't go into it. But it's very familiar. We get Bragg's law, 2d sine theta is equal to n lambda, right? D is the spacing between these planes. We get constructive interference only for certain angles of theta, which is known as the Bragg's angle for that set of planes. And lambda is the wavelength of the wave that is falling there. N is the order of diffraction. Old stuff. Most of us will be familiar with this. If not, you can brush it up. But this also is simply based on an understanding of the electromagnetic wave, of light being an electromagnetic wave. Okay? Light's wavelength is a little bit different, so you cannot use light to study the crystal structure. Because what are the wavelengths we are talking about for light? Yeah, what is visible to us, light is 400 to 700 nanometers, okay? And what is the periodicity of crystal structure? Roughly, when we say lattice constants, which we saw earlier for crystals, are we talking of 100 nanometers? Few angstroms, right? 5 angstroms, 10 angstroms, and so on. And so since light, the visible light is of a completely different range, we can't use that to study crystal structure. We need something that has electromagnetic radiation that has got much smaller wavelength, which is why we use things, as we'll come to later, X-rays and things like that, which have got much smaller wavelengths, corresponding to the wavelength, to the spacing of the crystal structure. So if we are talking of diffraction with visible light, then it must be diffracting off of something which has got hundreds of nanometers kind of spacing. All right, but the basic idea is the same. It applies to all electromagnetic waves, except it's not applied to studying crystal structure. That's the point I want to make there. But then there's a whole bunch of other phenomena that we cannot explain thinking of light as a wave. There's a problem, all right? And so we look at some of those. The only way we can understand light is by coming to a quantum picture. So there was the classical picture where treating light as a wave. I'll simply write that as a quantum picture. What is the basis of this? Light is not a wave, but it's a particle. Okay? Very radical. But then when you go back and think, Newton suggested something like that, the corpuscular theory. But it fell out of favor. But when you could not explain many other phenomena, it was radically again proposed that light is a kind of a particle in nature. It has got zero rest mass, introducing some of the relativistic ideas there. So it has no mass basically, but it is a particle. So because it is a particle, then it will have the properties of a particle in addition to other behavior that we see. This particle is referred to as a photon. Okay? And it's basically a packet of energy of light. And the energy packet or the photon cannot have any arbitrary energy. These are some of the radical ideas that were coming out. Light consists of particles, and these particles have energy, but they cannot have any arbitrary value. They are given by some multiples like this, where h, we'll see later again this term, a very useful number, Planck's constant. And nu is the frequency. So the energy is now dependent on the frequency. The higher the frequency of light, the higher is the energy of each photon that is coming in there. All right? Planck's constant, incidentally, has got a value of something like this. You don't need to memorize all these. 10 to the power minus 34 joule seconds. Associated with a particle also, we have a property called momentum. Every particle has some momentum, which is simply what? In simple terms, I give you a particle and tell it has momentum. What is it? It's the product of mass into velocity in its simplest terms for most of the particles. Now, we are not thinking in those terms exactly here, but we can still write P, which is momentum, is h by lambda. In terms of the wavelength, still we can talk about this. This is a very important picture that relates for me the momentum, which is a particle behavior, with lambda, which is the wave behavior. So in one equation, we are saying light is behaving like a wave with a wavelength, and yet light has got momentum where it is behaving like a particle. And when it was suggested, it's a very radical idea. And we will see that it is difficult to deal that is light really this or this. Is it a wave or is it a particle? And that argument went back and forth till consensus was more or less arrived at, that we'll just have to agree that it's both. Okay? But here in this one equation, we have the relationship between the momentum of a photon and the wavelength of a photon. Now let's look at some experiments that help to put a little bit more meat to this idea. For example, the photoelectric effect. In other words, why did people have to think of light in terms of being a particle? What was it that drove people in this direction, scientists in this direction? And it was that there are some experiments which simply couldn't be explained by thinking of light as a wave. And the photoelectric effect fundamentally is, we'll look at it a little more in detail, that when light is shining on a surface inside some evacuated material in an envelope, it emits electrons. Okay, photoelectric, light photo falling on it, and electrons are emitted from it. And we can measure how many are coming out and so on. And it had peculiar behavior, which we'll see. And it was actually Einstein who suggested the best explanation for this in around 1905. He offered the best explanation for the photoelectric effect. Incidentally, it is for this that he got his Nobel Prize. Right? Though he's more famous for what? Relativity theory. Everybody thinks Einstein, relativity. But actually, he got his Nobel Prize for this fundamental work. The explanation of the photoelectric effect is what he got it for. All right? What is this effect actually? Let's look in a little more detail. Suppose I take a quartz container, sealed and evacuated. There is no air in it. It's made of quartz. All right? And I got 2 electrodes in there. And I'm connecting it to some kind of a voltage source. So we have a cathode on one side and the anode on the other side. All right? And this is evacuated. It's empty. So if we put an ammeter in the circuit to be able to measure any current that is flowing through a circuit. So if there's no voltage that is applied, what would we expect to see on the ammeter? There shouldn't be any current flowing through it because this is empty space. There's nothing to conduct. There's no means to conduct it. There's no free electrons either there. So now we go and we put a source of light here. Then we shine light onto the surface of this cathode. And what we see then is that even when the voltage that is applied is 0, we are recording some current is flowing through the circuit. So the source of my electrons is not the voltage source here. It's coming from somewhere else. All right? The whole idea of putting a source like this, a battery, for example, is a source of electrons to drive the EMF that is applied. But here, even with this 0, the voltage source, I'm still getting current in the circuit. The only condition is that the frequency of light, in other words, I can't take any light and do, nu should exceed a critical value nu naught. So there is some threshold value or a critical value nu naught, and this light that I'm shining onto it must have at least that frequency for us to observe this phenomenon of current flowing in the circuit even in the absence of a voltage. Okay? Below that, we won't get it. Above that, we are producing the current flowing in the circuit. And what this means is that the energy of the light is being given to electrons in the cathode. Light has certain energy, h nu, and this is being given to the electron, which is then being pushed out into that empty space. This is positively charged. The electron is then traveling through and coming here and flowing in the circuit. Okay? What can we also do? I can now apply a certain voltage. So far we were talking with 0 voltage, right? I apply a positive voltage. And what we see is that the current flow increases as the voltage increases till we get saturation. So current and voltage, I apply a positive voltage there. The current flow is increasing, but after a while it simply saturates. Okay? If I change the intensity of the light, will there be any change to this picture? It's the same frequency, but it's more intense. Okay, some of you are suggesting nothing is going to happen. Others are suggesting maybe something will happen. It turns out, Okay. The current at which it will saturate increases. So we'll get. So you can look at it almost like, say, intensity 1, intensity 2. The higher the intensity, it produces a higher current and then saturates. Okay. So we see then that my saturation is limited by how many electrons are coming out of the cathode. That's what this indicates. If I can get more electrons to come out of the cathode, then it will be pulled out till it saturates. So the intensity is allowing me to regulate the number of electrons that are coming out, but it is still dependent on the threshold. I can put as intense a beam of light as I want with nu less than nu naught. It doesn't matter how intense the light is, it still will not produce any current. So only if nu is greater than nu naught and it satisfies that condition, then is this intensity going to play a role in regulating the current that is flowing. What happens if I apply a negative voltage to this system? All right, I flip the voltage around. What will happen?
Current will decrease.
Okay. And then?
After some time, current will be zero.
Current will decrease and after some time it will be zero, is what he said.
Means after some time means when you increase this.
So as the voltage, negative voltage goes on increasing, then the current in the circuit goes to zero. Is that what you're saying?
Yeah.
Does that make sense? Here I've got electrons coming in this direction, emitted from the cathode as the light is shining. I apply a negative voltage here.
There will be a charge accumulation.
Basically, it will start repelling, right? So what he's saying is that after some time, as the voltage goes on increasing, the field that is generated in the other direction will oppose the electrons, and finally you'll have no current flowing. So what will that look like in our figure of current versus voltage? We had, I'm going backwards, we had the saturation current, okay, and then it goes on, and at some voltage down there, which we call V0, it's current and voltage, we get absolutely no current flow through the system. It makes sense. The electrons are coming out, I apply a V0, and at some point it's all going to stop. Basically, the application of the field, when an electron is in the presence of an applied field, it has got energy, EV, right? The change in energy in the presence of a applied field. V is the applied field. Right? So when we have a negative voltage biased V naught there, then the change in the voltage is, in the potential energy is EV naught. So when we are having V naught here, what does that tell me? The potential energy change that the electron experiences in the field V naught is EV naught. And I have no current at V naught. What can I conclude from that about, say, the kinetic energy of the electron at that point? So it will be equal to that, right?
Yeah.
So whatever was the kinetic energy with which it was coming out of here has been equalized at V naught. So it has gained enough potential energy, or the energy, the kinetic energy with which it was coming out has been converted into potential. So it comes to a stop. There's no more current flow. So we can then write that EV naught, which is the potential energy change, is equal to half ME velocity squared. Half mv squared being the kinetic energy. So the maximum kinetic energy that the electron had is given by EV naught. That is the point at which it was released from here, and then it is slowing down, finally stopped. So this relationship here gives me what will be the maximum velocity that it can have. So if I can physically measure this value of V naught, what is the negative voltage I should apply in the presence of the light to stop the current flow, I have a measure of the maximum kinetic energy with which it is. So it's an experimental tool for me. I measure the negative voltage at which current stops. That means I know what is the maximum kinetic energy that the electrons have when they are emitted. Now note that this V naught, which we saw here, it does not depend on intensity. Okay? So it is not dependent on how bright the light is or not. That's the energy change. So the brightness we are seeing affects the numbers of electrons that are coming, but is not affecting the energy with which they are coming out. V naught is a measure of the kinetic energy with which they are coming out, not how many are coming out. Right? So if I change intensity, I'm not changing the energy. H, it's still staying at h nu, but I'm changing only the numbers that come out. So it will not depend on intensity. It only depends on frequency of the incident photon. Yeah. Okay. I affects, the intensity affects the numbers. So now I can do another experiment. I can take a variety of different metals and use them as the cathode. And then I make a plot here. I make different tubes like this with different metals, sodium, potassium, cesium, so on. And I measure, using an experimental setup like this, the kinetic energy versus frequency. And we can plot this then. Essentially, it's a plot of that V naught for each of the systems, because that is the kinetic energy maximum. Multiplied by E gives me the. So experimentally, I measured all the V naughts for these systems, and then I plot it as kinetic energy versus frequency. And it's interesting that they all seem to have the same slope. So if you take, say, something like cesium, potassium, and so on, they have the same slope. But the frequency, which is the critical frequency above which we will see something, is all different. Nu naught, that's, I'm just putting a symbol there, nu naught. Okay, I should probably write that bigger. Yeah, which is for cesium, subscript, and potassium. So the threshold frequency or the critical frequency is different for each of these metals, but they all have the same slope. And what is the slope going to be? Planck's constant. So here's an experimental tool for us to determine Planck's constant. Take a bunch of metals, fabricate a system like this. In fact, that's how Planck's constant was determined by a man called Millikan. Millikan's oil drop experiment, you heard? This guy determined Millikan's experiments. Anyway, Millikan was a fellow who used photoelectric phenomena like this to determine the value of H. So you have an experimental value there now. All right? We'll come back to this figure again. And we see that the kinetic energy simply depends for any given metal only on the frequency that we have. This expression can be put in a mathematical form. The maximum in the kinetic energy is equal to h nu minus h nu naught, where h remains the Planck's constant, nu is the frequency of incident photons, and nu naught is the threshold frequency. It's simply a y is equal to mx plus c type of plot, right? One constant term and a variable there that we have. So this is what Einstein's explanation was for this whole phenomenon. Or we may say the quantum explanation for this. Because classical behavior of light as a wave is unable to explain what we are observing. And so we need a quantum explanation. Here are some of the conclusions that were drawn. Light consists of energy packets, which we saw earlier. Called photons. I began with that, but this is some of the conclusions that were drawn from an experiment like this. Each photon has energy given by h nu. And then he said, when the photon strikes the cathode, strikes an electron, it transfers all the energy to the electron. Okay? And now remember, because we have only certain fixed values of energy, only fixed quanta of energy can be transferred to the electron, not any arbitrary value. Now remember, in a metal, the electrons are at a lower potential than if they were in vacuum. So you have to give some energy to pull it out of the metal. Otherwise, it would simply be coming out all the time without our doing anything. The very fact that the electron is staying inside means that it is at a lower energy there. Otherwise, we would be getting spontaneous emission of electrons out of a metal, which would be very nice if you could just have a metal, put it there, and electrons keep coming out. Many applications I can think of. But electron has lower PE than in vacuum. Okay? And this is what we call the work function, the energy that is required to take it out of its, in the metal, into vacuum. So you can think of it as a barrier for the electron that it has to surmount before it can be free. It's called the work function. Okay? So when the quantum of energy is given to the electron, what happens to that energy? The photon had a quantum of energy h nu, and this is transferred to the electron. What's going to happen first? It has to get across the barrier first. That is the minimum energy it requires to even get out of the place. All right? So what's the energy that is left? H nu minus phi is the energy that is left when it has reached here. H nu was given to it. Phi is used to climb the stairs and get out of the place. And now it has got h nu minus phi. What is h nu minus phi then? The kinetic energy. It has got this much energy left, which is simply the kinetic energy maximum. Okay? So now when we go back and compare it with what we have written here, I've reversed it. What do we see? What is phi equal to? Phi is equal to h nu naught. You can see that there, right? H nu minus phi. So phi is simply h nu naught. So if my model is true, I can experimentally measure nu naught, what is the threshold frequency at which I get current, and that should be equal to my work function. Now there are other ways of measuring the work function of a metal too. It's an experimental parameter. We'll see that later. And it was seen that the value that was obtained by doing a photoelectric experiment like this for the metal, by measuring the threshold frequency and then calculating the work function of the metal, matched quite well with the value that was obtained from other sources, suggesting that this model of the energy transfer of the photon to the electron and it having to surmount that and thereby have a certain kinetic energy was valid. So it's very good accuracy. We can get the work function of the metal comparison with the value that is obtained from other sources. So this was a great explanation that allowed scientists to make tremendous progress. It held up because wave picture simply cannot explain this. So Einstein's suggestions along these lines was very interesting. In fact, this guy Planck used similar ideas to explain emission from a black body. Okay? And I think it was that inspired Einstein. I'll just take a brief diversion there. You know what a black body is, right? Perfect emitter of radiation. So the radiation is coming out with a number of wavelengths. If you can measure what the radiation is coming out and plot it as a spectrum, intensity versus wavelength, we'll see some kind of a spectrum. And people found it very difficult to understand the spectrum of the black body, why it behaves in a certain way. And it was Planck in around 1900 who proposed that the energy is also quantized that is coming out. And it was these ideas that finally led to the great quantum mechanics that we have today. Trying to explain some simple phenomenon like that, a hot body emitting radiation, why we see only certain frequencies and so on. And the idea was suggested that it is quantized. And these are the ideas that were later on taken by Einstein to explain the photoelectric effect, and then further down by Bohr to talk about the atomic structure, which we'll come to later. Okay? So now we have an explanation for the photoelectric effect by treating light as a particle. Now, if light is a particle, how do we talk about its intensity? What is the intensity of a particle? I can't use that old expression that I had, half c epsilon naught electric field vector square, the amplitude square. So now if I'm saying that light is a particle, what is its intensity? And so we can talk of intensity in terms of the number of photons that are coming out. Our definition of intensity was what earlier? Electrons, the energy flowing per unit area, per unit time, right? So I define a flux, number of photons per unit area, per unit time. That's the flux of photons. And then if I want the intensity, what do I need to do? Photon flux is given by this, and intensity is the energy per unit area per unit time. So, very good. So if I want intensity, all I need to do is multiply it by h nu, because each quantum is h nu, right? So now when treating light as a particle, we use a different definition of intensity by treating it in terms of the photon intensity times the energy of each photon. So here we have now a picture of light as a stream of particles that are traveling through space with a velocity c. Back again to Newton. And Newton was, I sometimes look back and I say Newton was probably way ahead of his time in suggesting the corpuscular theory. He suggested there were red corpuscles, green corpuscles, and so on, right? It sounds funny to us. There's a red particle of light and a green particle of light and so on. But when you look at it, you see each of these wavelengths of light, the red and the green and all are so different. So effectively, a quantum of red light is different from the quantum of green light and so on. So he wasn't completely foolish in suggesting there's a red corpuscle. His ideas were old-fashioned. He was thinking in terms of distinct particles. And now we have a refined idea here. And so we come to the quantum ideas. But the question still remains, do we talk about light as wave or as particle? And we see that we have to treat it as both. Whenever it is convenient for us, we call it a wave. When it's convenient, we call it a particle. It seems silly to do that because we are trained to think that we need some resolution. Somebody has to decide. And perhaps another theory will come along which allows us to reconcile this better. Here's another experiment that was done in that time. One example I gave you is the photoelectric effect. Another is called Compton scattering. In this case, we take an X-ray and it strikes an electron. All right? An X-ray beam with a certain frequency and a corresponding wavelength strikes an electron. What happens to the electron? Energy is transferred to that electron, and so the electron gets scattered. So we could draw the electron that is scattered here. It is scattered off at some angle phi. But the X-ray beam itself, which came in, is scattered with an angle theta. And now if we can measure the frequency of the X-ray that is scattered, we will see that it is no longer nu, it is some value nu dash or lambda dash is the change in the wavelength. And what we observe is that nu dash is less than nu. In other words, some of the energy of the X-ray which was given to us by h nu has been transferred to the electron, and h nu dash is the new energy of the X-ray. And we can also obtain that the kinetic energy of electron, we can measure that, how it has changed, and we find that it is given experimentally by h nu minus h nu dash. So the difference in the energy, if we measure the kinetic energy of the electron, we see it has simply been transferred to give kinetic energy to the electron. Now this electron is a particle. Okay, this was the other reason why we have to start thinking of electromagnetic rays as particles too. Electron is a particle. So electron has a momentum, that is understood. So when an electron is having a momentum and there is momentum change taking place here, we have to talk about conservation of momentum in this system. The electron had certain momentum here, now it is moving, there is change in momentum. So from the ideas of conservation of momentum, we are forced to conclude that some momentum change is also taking place in the X-ray. And momentum is a word we are associating with particles. So here was another reason to come back to it and look and say, well, an X-ray is probably a particle too. Okay? Because of this kind of scattering experiment. And we can associate, as before, then the momentum of the X-ray as h by nu. All right? The actual experimental setup by which this kind of experiment was done looks something like this. I just gave you the outline. There's a source of X-rays, and we pass it through a collimating slit. So we get a fine parallel beam of X-rays coming there. And the wavelength is lambda naught. It hits some kind of a conducting target. Okay? Say, for example, a thin sheet of graphite. And part of the beam is then transmitted. Wavelength we detect as lambda naught. But we find that if we move the detector around and measure the intensity and wavelength as a function of angle, we will see that we will get also scattered X-rays with a different wavelength. So experimentally, this is how this Compton scattering experiment is done. I get the transmitted beam, which is the original beam itself, but I also get, as I check the change in intensity as a function of angle there, I will get for different angles, I will get different values. If I plot for theta is equal to 0, I will get some peak like this. All right, that's just the transmitted beam. And the wavelength that it is centered on is lambda, intensity versus lambda, for example. And if I bring it down to 90 degrees away, so theta is equal to 90 degrees, I find a change in the profile, where now I have at some other wavelength lambda naught, I'm sorry, this is lambda naught, the original intensity, at some other wavelength lambda, which is longer, that means it has lower energy, we find there is another peak there, and so on. And the only consistent explanation for this phenomena as it was done was that the X-ray is behaving like a particle and the momentum is changing. So from these kind of experiments, this was the idea that was derived, that the X-ray, which is also an electromagnetic wave, is behaving as a particle with a certain momentum. So we can summarize this idea here for light. There are more experiments like this that were done actually before people, because it is such a radical idea, it took quite a lot of convincing. But ultimately it was concluded that light has a dual nature, and we can write the behavior in terms either of its wave nature or in terms of its particle nature. And it is this equation that relates the two. P is equal to h by lambda. You can express this in other words also, which we started with. Okay, it's the same thing, the energy expressed in terms of omega. And what is h by 2 pi? How do you express that? We write that as h bar, right? H bar omega. And similarly, P is equal to h bar k. So expressing the same thing either in terms of frequency and wavelength or in terms of angular frequency and wave vector. So now light is a wave that behaves as a particle. Let's take a few minutes to look at the electron, which is a particle. Everybody agrees that the electron is a particle, and there were experiments that were done to demonstrate its particle nature way back. You put a little fan-like thing and impinge electrons in a vacuum. The fan starts rotating because there's momentum transfer from the electron to the fan, a metal blade, basically. So it was evident to everybody that electrons are particles, and even in the old picture of the atomic model, the electron was always treated as a particle of carrying negative charge that is there. There were different ideas about where it was located, but it was always treated as a particle. And then we were confronted with some situations, for example, electron diffraction. How do you explain electron diffraction if an electron is a particle? You remember I showed you some of these pictures earlier. I'll just put that back up for you to see. Do you remember this picture? I told you that this is from a sample where we put a very thin sample in the path in a vacuum chamber in the path of an electron beam, and then the electron passes through it. And we can create an image out of it, or we can look at a diffraction pattern. And the fact that there are spots there tells me that we have single crystalline specimen. Okay? This is being produced by the diffraction from the planes. And I told you that if there is polycrystalline nature, we will see rings. You can see a main circle there. There are fainter rings that you may not be able to see, but at least you can see the innermost circle. Actually, there's 2, 3, maybe 4 or 5 rings that are there. It's very faint. And the rings indicate that in this sample, we have a polycrystalline nature to the sample. All this is simply telling me that the electron beam that passed through the sample got diffracted, because these are diffraction patterns. Now, if electron is a particle, how do we then explain diffraction? So people were then led to conclude that an electron is also a wave. It has wave behavior. All right? So because of the effects like this, of the diffraction patterns and so on, you can again use Bragg's law, 2d sine theta here is equal to n lambda, to explain the diffraction here. So it's behaving exactly as if it is like a wave. And so then the conclusion was drawn that the electron is also behaving as a wave. Again, back to the wave particle duality. So we can calculate its momentum, which is equal to, from the momentum, p squared by 2m, what is that term? Kinetic energy. Okay? So the electron is coming through this material. Electron has got an applied, it is emitted, it is across a field V, that is the applied voltage in the electron microscope, for example, and that is being converted into kinetic energy. The potential energy is getting converted to kinetic energy. And so from this kind of an idea, we can calculate again lambda. I should write it again. Lambda is equal to h by p. So from 2d sine theta, knowing that I've got a certain kind of plane from the angle of scattering and so on, I can calculate a lambda value for the electron beam. Right? And I also know, if I know lambda, I would know its energy. And here I've got, from the applied voltage value, I've got momentum values. So I can relate all this, and we come to this equation. Just the opposite of this was written earlier. Right? We had for light, we wrote P is equal to h by lambda. It's the same thing. And this famous equation is known as de Broglie's equation. So it relates for both the electron as well as for the light, for the electromagnetic waves, the wave nature with the particle nature. We can use these ideas to see how absurd sometimes it might be when we talk. Does de Broglie's equation apply only to electrons and waves, or does de Broglie's equation apply to all kinds of objects? To all kinds of objects, right? So we can make a simple calculation to see what it, say for example for an electron beam. So what will be its wavelength to give us an order of magnitude estimate? I have an electron that is accelerated by 100 volts inside the microscope. Okay, I want to calculate what is the wavelength. I have de Broglie's equation. I also know the kinetic energy related to EV. V is 100 volts. I know the mass of the electron and so on. And so now I can go back, calculate P, and put it back in here to get an estimate for lambda. It turns out that lambda is equal to 0.123 nanometers. That's roughly 1.23 angstroms. Not roughly, that is 1.23 angstroms. Okay? 1.23 angstroms now is of the order of the crystal spacing. Remember, we said that crystal spacing is of the few angstroms. So that is why we are able to use an electron beam to get these kind of diffraction patterns, because the crystal spacing is roughly of the same order of magnitude as the electron beam wavelength. And that is why it diffracts. Otherwise, we wouldn't get diffraction effects from it. Now let's take another more current example. A cricket ball. It's World Cup time, right? So we've got to talk a little bit about cricket also. I don't know the official prescribed weight of a cricket ball, but let's say it's 100 grams. Maybe I'm way off target, but I don't know. I'm just putting a number. How much? 169. We got the cricket expert. I'm taking 100 for simplicity. It's just 100 grams. And there's a fast bowler, he's able to throw it at 110 kilometers per hour, which roughly, for simplicity again, I approximate as 30 meters per second. Okay? So we got this 100-gram cricket ball traveling with a velocity of 30 meters per second. We want to know its wavelength. So again, we make a calculation. What do we get? It comes out to be about 2.2 into 10 to the power minus 34 meters. And that's the wavelength of the cricket ball that, who's our fast bowler these days? McGrath? Australian fellow? He's not bad, no? Huh? Brett Lee, all these guys, maybe they're able to pitch. And the ball is traveling with a wavelength, if we treat it as a wave, of 10 to the power minus 34 meters. So when it is traveling, we can't measure something like this even, right? So we wouldn't expect to observe diffraction of a cricket ball. Now I'm tempted to suggest that the in-swingers and the outswingers are like diffraction. They're coming and then they're zooming off. But really that is not the case. So this is really, we don't for macroscopic objects, this is only for a 100-gram object. You also have a wavelength which you can calculate, and it will be even smaller than this because the mass is even larger. Most of us are heavier than 100 grams. So we have even shorter wavelengths. So that is why, even though the wave-particle duality, de Broglie's equation, applies to all of us, all objects, what is observable as phenomena is only taking place for the shorter, for the very small